MECH2410 Engineering Materials. Tutorial 6 Failure of Materials. There is no perfect materials in this world, and as we know that for any real-world materials, it can only sustain a finite value of stress before it breaks. So, if the applied stress exceeds some critical value, any materials will eventually fail. For example, in the uniaxial tensile test, if the applied tensile stress exceeds the ultimate tensile strength for that particular material, the material will eventually break. And just like what I have just written in this PowerPoint, the bars at uniaxial tensile test will break at the end of plastic deformation region if the stress exceeds the ultimate tensile strength. So in this video, I would like to introduce what are the types of the failures and how can we determine the conditions for material failure. As we are mechanical engineers, we must have the ability to identify under what situation a particular material will fail or it will break. Tutorial 6, Part 1, Fracture Types. There are two types of failures, brittle failure and ductile failure. Brittle failure is a low energy process and it is very quick. As its name suggests that brittle failure only happens for brittle materials, such as glass. For example, if you throw a glass object into the ground, it will break. And as you can observe that when you touch the ground, the propagation of those cracks is very, very quick. And eventually, the glass will broken in pieces. However, for ductile failure, as its name suggests that it is for ductile materials, and it is a high energy process, and the time required is large, and it is larger than the time required for brittle failure. For example, if you try to scratch a rubber band, the rubber band will not break easily, just unlike those glass, and you need a lot of energy to really break the rubber band into two or more pieces. The example I have just introduced are just some general examples. So how can we identify a material to know whether the material will undergo ductile fracture or brittle fracture? Actually, we can identify this by looking at the features of the broken samples in a uniaxial tensile test. For the specimen in the uniaxial tensile test, there is several modes for the failure. The first one is the brittle fracture. The second one is the ductile fracture. And the third one is the completely ductile fracture. Basically, all materials will fall into these three categories. For A, the main feature is basically at the broken position here, the deformation of the materials here is minimal, and the percentage reduction of areas at the broken position, or the percentage elongation at the broken position is very small for the percentage elongation and the percentage reduction of area. For ductile fracture, you can see that the main feature is near the broken position, there is an elongation and there is a deformation of the materials. And you can see that there is a area reduction and there is a elongation of materials here. And as you expect that the percentage of area reduction and the percentage of elongation will be a number larger than A or brittle fracture. For C or for third one, it is completely ductile fracture, and at the broken position, the material deformed completely, and as you expect that the area of reduction and the percentage elongation will be the largest among these three. For a material undergo a uniaxial tensile test, after the string hardening region, which is at this position, the point D, the necking will start. Basically, at some parts of that bar, the diameter of that particular position will start to contract, just like the picture A. And at the necking position, it will fail. For ductile fracture, which will be described in these pictures, after the necking, there is a formation of microvoids. Basically, it is a small, very small cavities, which is picture B, after necking, which is picture A. After the formation of the microvoids, they will merge with each other to form a crack, which is picture 3. And after that, the crack will propagate in picture D. And finally, in picture E, there is a final shear fracture at the 45 angle relative to the tensile direction. The 45 angle is a special number for such kind of fracture because at this angle, it is the easiest position for it to break, basically. And it has the largest stress along this direction when it is subject by such uniaxial loading. In the previous slide, I have described the ductile fracture process. However, for a brittle fracture process, it is very different from the ductile fracture process. The first thing is, when we try to look at the stress strain curve for a ductile material and for a brittle material. For brittle material 1, there is no necking regions, and the fracture position is at the maximum stress position for that particular brittle material, unlike for ductile material. So, therefore, there is no necking for brittle fracture, definitely. And as there says, it is a rapid cracking process without much deformation. And during this process, there will be a cleavage, which is a direct separation of the atoms on a low energy crystallographic planes. And by such direct separation of the atoms, there will be crack propagation along those planes. After the separation of atoms and the crack propagation along these planes, you can see on the cracking surface, there will be river pattern or chevron markings on these surfaces, which is different from ductile fracture, which cannot be seen in ductile fracture. How the crack propagates within the material is also a point of interest for our study. There is two fracture types where we characterize the fracture types in terms of how the crack propagates within polycrystalline solids. The first one is the transgranular fracture, and the second one is the intergranular fracture. For the transgranular fracture one, the fracture cracks will pass through the grains, which is such process is for most brittle crystalline materials. But for intergranular fracture, the crack propagation will be along grain boundaries and it will not pass through the grains. And such process will happen in some alloys.